All right, hopefully that's works reasonably well. All right, so a question like cosine of 6x, cosine of 4x dx, right? Something like this is basically screaming for us to use one of those formulas that we were talking about just a moment ago. So let's go quickly look up the cosine addition formula. Yeah, cosine addition formula. And what do you know? It's basically, okay, so it can be written in a couple different ways. Let me actually use it in the format that you gave it to me, okay? So Irvine students, so you basically gave me that cosine of A times cosine of B is equal to 1/2 cosine of A minus B plus cosine of A plus B, right? Now, I always think it's good to talk about the motivation before charging headfirst into a calculation. And the motivation here is you have a cosine 4x and a cosine of 6x. I don't know how to do this directly at all, right? I can handle cosine times cosine if they have the same argument. But as you'll learn if you go further in math, when cosine and another cosine have sort of like different constants here, they're just at totally different like so they're like totally different frequencies, and in fact they're kind of orthogonal to each other. They're very hard to manage. But using this identity, we can get this in terms of a single cosine plus another single cosine, and we can separate those out and integrate them independently. And that's why this is so nice and so clean, right? Okay. So at this point, we're basically saying, okay, let's just match this up. 6 is A and 4 is B, right? A is equal to 6, B is equal to 4. So then this just becomes 1/2. What's up?
Oh, yeah. No, keep going. Sorry.
Sure. 1/2 cosine of what's 6 minus 4? That's 2x. Sorry, I guess it should be 6x, 4x. Plus cosine of 10x, right? 6 plus 4, 10x. And this is totally something you know how to do, right? At this point, you just need to remember to use chain rule. And that's about the only subtlety here, right? You got to divide by 2 because there's this 2 here. And I think you got to divide by 10 because there's this 10 here.
Okay.
Sound about right?
Yeah.
So as for these formulas, I don't know how to motivate these formulas off the top of my head. I think you just got to look up the 3 product identities and just here, I'll display it on my screen very briefly for people who are wanting to watch me a stream, but or a recording. But you just basically got to look these up and burn these into your memory. Sorry, I don't know a better way to do it than that. It's not. Yeah. Okay. Do you want to do the other example as well, or do you think you've got it? These problems, once you have the formula, it's really not that bad.
Okay, so the final answer is like sine 2x over 4 plus sine 10x over 20 plus c.
Yeah, I think that's right.
Okay.
I think that's very good.
Okay, yeah, I understand these formulas now.
Sorry, what'd you say?
No, I said I understand like how to do like these types of problems.
Gotcha. Yeah. So the other problem, I'll just write it out, but I won't explicitly do it, is sine of 4x plus times cosine of 2x, right? And it's the exact same idea, just use a different formula for it. But you're basically going to want to add, use one of those formulas that turns a product of trig functions into a sum of trig functions. And that should take care of it for you.
Okay, I get it.
Yeah. So let me ask you this. If you've ever seen a problem where it's just like cosine squared of x, this is just equal to cosine x times cosine x, right? If you write it this way, do you think that these formulas would help you out?
Yeah, because I usually I always expand them. Unless I use U sub, I usually expand it when I write it down.
Yeah. This actually just turns into the double cosine angle formula, which in fact does help you out all the time, right? It's just a simpler way. Like so this isn't an explicit problem, but it's good to know. How would you integrate cosine squared of x? This is something that I think you should probably have down, down cold. So this is a situation where we don't have the extra sine of x to make our life easier, right?
Yeah.
So how would you integrate cosine squared of x?
I don't know.
Yeah, no, it's okay. It requires one of those identities, one of those double angle identities that we were talking about.
Yeah, the 1/2.
Exactly.
Yeah,
so in fact, we can rederive it from this equation, right? Like if this equation is given to us, if a and b are the same thing, right? So that's basically, if a and b are the same thing, this is just cosine squared of a, right? And that turns into, if a equals b, this turns into 1/2 of cosine of a minus a is just 1, right? Cosine of 0 is 1, plus cosine of 2a, right? This is one of those identities you see from high school. Cosine squared of a is equal to 1/2, 1 plus cosine 2a. And I think just rewriting that, if I'm not mistaken, cosine squared of x is equal to
1/2, 1 plus.
Yeah, I might have made a sign error, but hopefully not. Yeah, 1/2, 1 plus cosine of 2x over 2. The way that I typically remember this is that cosine of 2x is equal to cosine squared. This is the one I actually remembered, minus sine squared of x. And then I remember that cosine squared plus sine squared is equal to 1. So if you sub in for minus sine squared, that's cosine squared, is equal to cosine squared minus 1 is equal to sine squared, minus sine squared. And that turns this into 2 cosine squared fx minus 1, right? So cosine 2x is equal to 2 cosine squared fx minus 1. You add the 1 to the other side and divide by 2, and this is what you get. Am I going too fast? Is this confusing at all? This is all technically a review from high school, but this is the moment when it actually comes in handy. Hi, are you still there?
Yeah, I'm still here. I don't know why my mic like turns off sometimes. It's all right. Like I understand it.
Okay, you're feeling good? Good.
Yeah, the pacing okay also.
Good, okay. So then, well, why is this nice? Why did I go through this entire, I asked you how to integrate cosine squared of x, and now we can rewrite it as integral of 1 plus cosine of 2x over 2. This isn't a trick question or anything. Why is this nicer than before?
It's easier to, like, you can bring out the 1/2.
Yeah, sure. Well,
and it's cosine 2x already.
Sure.
So,
We're adding them together, so it's not really bringing it out so much as it is separating the integral. But yeah, this just turns into cosine of 2x. Oh, what the hell is happening with my screen? But yeah, this is just a basic trig integral, right?
No, I meant like you could bring out the 1/2 from the cosine 2x over 2. Like 1/2.
Oh, this 1/2? Sure. Like I said, that's not really a big deal in my opinion. Whether or not you have the constant out here, inside or outside, it's really not a big deal. It doesn't fundamentally change what I would call the like difficulty of the integral, so to speak.
Yeah.
But fundamentally, this is just the most elementary of trigonometric identities, right? Trig integrals. It's just that this extra 2 you have to account the chain rule, right?
Yeah, it's sine 2x over 2, right?
Yep. So this would turn into sine of 2x, and then the 2 would come from over, because of chain rule, you would get divided by 2, but then you would get another divided by 2, so it's sine 2x over 4.
Yeah.
And then x over 2 here.
When you're integrating the constant beside the variable, you bring it down. But then if you're deriving, you put it up, right? So if you're deriving
Sure.
cosine 2x, it's gonna be 2 cosine 2x.
If I was to take the derivative of cosine 2x, so you're asking me this?
Yeah.
Cosine 2x. This would be minus 2 sine of 2x.
Okay, minus 2 sine 2x.
Right.
Okay.
The cosine turns into a minus sign, and then the chain rule, the 2x, the 2 in front of the x gets bumped out. Front. That's where it comes from. But you can always take a sanity check, right? Once you take a derivative, you can always check to yourself, okay, sanity check. If I was to go in the backwards direction, if I was to take the derivative, would it spit out cosine 2x? And it would, because sine would change to a cosine, and the 2 would bump out here, which would cancel out with this 2.
Oh, okay.
Right?
I see.
So always do a sanity check afterwards, and after you take an integral, go backwards to make sure the derivative would have ended you up back at the starting position.
Okay.
So that's great for simple things like this, where the only complication is like a chain rule or something. Like if this is like some incredibly nasty if this is some incredibly nasty integral, then don't bother, right?
Okay.
But if it's just some like cosine or a tangent or something relatively simple that you want to sanity check. Okay, tangent's actually not that simple, but cosine, a sine, or any of the elementary identities that just has a little bit of a chain rule scruple in there, always go back. I would say always go backwards to double check that you did chain rule correctly.
Okay.
Yeah. Okay. I've got more problems. How do you feel? We could.
Yeah, I can do more problems.
Okay, we can continue doing problems. Do we want to look at? So the other student from Irvine shared a big page of practice problems for their upcoming midterm. Do you want to take a look at those?
Where did they get that? I don't have it.
I don't know. I think she just said that her professor shared it with them.
Yeah, we don't have this.
Where did I put it? Gosh, there was this other student in here.
Trigonometric integrals, right? The Math 2B worksheet 9. I don't have that. But okay.
Yes, Math 2B worksheet 9. Where is that in? What chat?
It's in Calculus 2. It's sent by Huevos.
Gotcha.
At 5:40 p.m.
Okay. Oh, right. Okay. Yeah, let's open it up. So I actually worked through this a little bit earlier, and so I'm going to put like Calc 2B worksheet 9 in big letters. So hopefully if they watch this in the morning, they can use this to study for their midterm at 5 p.m. Okay. Do you want to just go through the list? Each one of these is a bit of a different concept and should, I think, should do a pretty good job of giving you some coverage of some stuff.
Yeah, I think number 4 isn't part of the exam though. Is it?
Number 4?
Yeah, average value. Oh, no. Okay, because they're taking the midterm. Never mind.
Yeah. Let me know if some problems don't look relevant. But most of these are trig subs.
Yeah, I think the number 4 is relevant to them. It's just not relevant to me because I'm not taking the midterm yet.
Okay, sure. I mean, it's really not that different of a problem. They're just wording it slightly differently.
Yeah.
It ends up being a trig sub anyways. So how do you want to do this? Do you want to just go down the line or what?
Wait. Number 4 is a trig sub. How do you do that then?
Number 4? Okay, sure. Yeah. Number 4, let me check my notes. It is indeed a trig sub. You might think that it's a u sub at first because it's an x squared and an x, but the x is unfortunately on the bottom. Right? I see, so it's not quite a u sub, or at least I wasn't able to see how it would be a u sub. But the idea here is, okay, we have something squared and a constant in here. This should be screaming one of our trig identities, right? This should be screaming one of our trig identities. We just need to remind ourselves which one. So let's write it out. Cosine squared theta is equal to 1, or tan squared plus 1 is equal to secant squared. Which one does this look like to you? The
sine squared. The sine squared one. The secant. No. The secant.
Don't just guess. Justify it.
One, right? Because you minus 1.
Yeah, that's right. So tan squared of x is equal to secant squared minus 1. Right? So we get this really nice correspondence between the x squared and the secant squared and the 1 and the 1. Yeah. So this is a case where we don't even have to mess around with the constants or bring anything out like the earlier example we did, which was before the recording. So this one, we can basically just go charge right ahead. Yeah. So we want to make, I'll just write it up here just to show the correspondence again. But we're trying to make let's call it secant squared of u. Okay.
Yeah.
This one needs to correspond with x. So this is basically saying secant of u is equal to x. So what's the derivative of secant?
No. Tan secant.
Tan secant? Is that what you said?
Yeah.
Yeah, that's right. Yeah. Unfortunately, this is just something you got to memorize and know down. Have.
Yeah, I just have to
know down cold. So this is tan secant. Okay. So let's see what happens when we plug this in, right? So the integral of, secant, now it's secant squared of u minus 1 gives us a tan squared here, right?
Yeah.
And what's in the bottom? The bottom is just now a secant of u. What's dx? Dx is now tan of u, secant of u, du.
Okay.
Look good so far? We're going to get a bit of cancellation. What's up?
No. I mean, you're gonna cancel the secant.
Yeah, so I think the secants cancel out, and tan squared, square root of that is just a regular tan, but then it gets multiplied with
Yeah.
another. So I think this is what it looks like, right? The square root of tan squared
Yeah.
u du. Is that right?
Yeah.
This is unfortunately, this is actually a little bit nasty. But you just sort of gotta go through it. So tan squared of u is what is that? I wrote it up here. 1 minus secant squared, right?
Yeah.
Actually, sorry, that's probably not the best way to do it. Okay, so we're getting to the point where it requires probably just some memorization.
Yeah.
Because technically, tan squared is secant squared of x minus 1, right? Du. And if you remember correctly, secant squared is actually in a elementary integral. Do you remember what's the derivative of, what's the integral of secant squared?
Yes, but I can't recall it right now.
Sure.
Yeah.
Yeah, it's tan.
Okay.
And this should be a u, I believe. A tangent of u. So, gosh, you see how tricky this was? Like, we went from tan squared to secant squared u minus 1 back to tan.
Yeah.
But that's just how it is sometimes. So I think that's tan u minus u, right? And that goes from I won't do the bounds. I'll wait until we resubstitute it to do the bounds. In fact, I'm sorry, there are no bounds on this one, so you don't even have to worry. It's just plus c, right? So as always, at this point, I like to draw a triangle. And what was our... Do you understand why I always draw the triangle?
Yeah, because you're looking for the...
Yeah. I have the relationship that secant of u is equal to x.
Yeah.
And now I need to turn the u's back into x's. So if secant of u is equal to x, I draw the triangle and say, okay, well, what's secant? Secant is hypotenuse over adjacent, right? Yeah. So this is x, this is 1, and by Pythagorean theorem, this is x squared minus 1. Yeah? So tan just becomes square root of x squared minus 1.
Sorry, my brother's playing games.
No, it's okay. I'm a little bit nervous right now because I felt like I had when I was working this problem earlier, there was a natural log here somewhere, and I'm worried that I missed this. Let me plug this into an integral calculator really quick just to do a sanity check. I think I might have accidentally stumbled somewhere. You know, I make mistakes too. I've never been that great at calculation. Square root of 1 plus x squared divided by x. Let me take a quick look here. Sorry, I realize I'm not sharing my screen, but
no, it's okay, it's okay.
Yeah. Wait, this is bad. What was my work earlier? Yeah, I'm pretty sure it was fine up to one of these steps, but where did I go? X squared plus 1. Yeah, this is always the hard part about trig substitution, is that if you make a minor mistake, it can look wildly different. And I'm going to double check my work from earlier because I was working this out with somebody else. Gosh, where was I? Oh yeah, it was this one right here. Yeah, someone was asking me this problem, right? I might have just made a really stupid computational error, to be honest with you.
It's okay.
Yeah, let me double check this. I think I need to just be very careful about... Okay, let me just... Oh, I'm sorry. I got problem 4 mixed up with problem 1. My bad. I was remembering the answer to problem 1, and that kept making me feel like I was doing something wrong, but I think this is fine.
Oh, problem 1 has...
Problem 1 is really nasty, and for some reason that one was lingering in my head, but I think this is fine.
Okay, wait, super dumb question.
Sure.
The ln is because it's 1 over x, right?
What's up?
There's an ln because there's a 1 over x, right? Like when you
The integral
look.
of 1 over x is equal to ln of x plus c.
Yeah. Yeah, that's why there's an ln, right? Like you were saying there's an ln.
Yeah, okay, so I
Somewhat
don't
like
want to
that.
quite say yes, because when you shuffle things around with trig substitutions, everything gets wonky, right?
Yeah.
That like x, I think, ends up getting absorbed by something else or canceling with something else.
Oh,
But
okay,
one
okay.
way or another, the ln does appear in that problem. And we can work that one afterwards if you like.
Okay,
But I'm
okay.
pretty sure this one is not that bad. This one is x squared minus 1
Yeah.
minus, well, what's u? U can be expressed in a bunch of different ways now. You could call it like you could call it the arc sine of square root of x squared minus 1. Sorry, there's a bunch of ways to express u, right? You could say sine of u is equal to square root of x squared minus 1. You could say cosine of u, x squared minus 1 divided by x. You could say cosine of u is equal to 1 over x.
Yeah.
This is probably the simplest, right? This means that arc cosine
Yeah.
of 1 over x is equal to u. And I would just plug that in right over there, and boom, we're done.
Mm-hmm. Okay.
So
Okay.
just to be super explicit, oh, I missed. I missed. I meant to say plug it in right over here. So arc cos 1 over x plus c. Yeah?
Yeah.
Okay.
Yeah.
Feeling good about this process?
Yeah.
Okay. I would say that see if you can work through, either these problems or an extra set of problems on your own afterwards. But you'll have these videos as sort of guidance if you want to see the process explained. Watch them at 2 times speed or whatever if you need to.
Okay.
But looking at these problems, do you want to choose the next problem? Do you still want to do problems?
Maybe number 6.
Number 6.
But then for number 6, can you also use the formula earlier when you were saying the cosine addition thing?
Yeah, that looks like a really good. That looks like a really good candidate for me to for cosine addition. For me, I did it with the double angle formula because I noticed that 5t and 10t were perfectly one. It was the half the other. So I would say the double angle formula is probably your fastest shortcut there.
Okay. And that's like half of the other. Then
yeah. Do you want me to show it out real quick?
Oh, okay, sure.
Sure. Okay. So cosine. My handwriting is bad enough on regular paper, but it's even worse on a OneNote. But the idea is, what did we see the expression was earlier? Cosine of 10t is going to be equal to, was it 1 plus cosine squared of 5t over 2? Is that what we said? Or did I lie? I lied. It should be. What? It should be 2 cosine squared minus 1 over 2.
Oh, okay.
Is that?
Why?
Let me just. Okay, I just feel like I need to write it out. So cosine squared minus sine squared, right?
Yeah.
Cosine of 2.
Oh, no. Okay, I get it. Sorry.
Right. So, no, I did make an error. So this is equal to 2 cosine squared minus 1. So this over 2 is incorrect. So it's good that you brought it up. Right. This sounds right because minus sine squared is cosine squared minus 1. And then you add that together with cosine squared, you get 2 cosine squared minus 1.
Yeah.
Right? So at this point, you just plug this in. And do you see why this works out so nicely? This turns into a sine of 5t, cosine squared of 5t. Remember that pattern we were talking about earlier? How this is a power of 2 and this is a power of 1, and it's just beautiful.
Mm-hmm.
And then I think it's a, if we expand, so this has a 2 factor of 2 in front of it. And then I think it's just like a, what do you call it? Like a sine of 5t dt by itself. And these are both perfectly beautiful integrals, right? This one, you just let u is equal to cosine 5t. Du is equal to minus sine 5t times 5 because of chain rule. And then, the integral is beautiful. Right?
Okay, I see.
Okay, good.
Yeah.
So you could have definitely done this one with the product formula if you so choose. Let me double check just to make sure it's a good fit. This was under Irving students, right?
Mm-hmm.
Yeah, no, I think this would have worked just fine with that first product identity as well. Sine A, cosine B, right?
Okay. Yeah, yeah, yeah. I see.
Yeah.
I see.
It would have been
Okay.
exactly the same
Yeah,
thing as the double angle. The thing that I did, just a little more general, so to speak.
Okay. Okay.
Yeah. Like, for example, this one still would have worked if this was sine. What I mean by that is the double angle formula is just nice and convenient because it's perfectly double. The one is perfectly double the other. If this was 5t and
Yeah.
12t, for example, I would have had to resort to
Then, yeah.
the general
other one
formula.
would be better.
Yeah,
Okay. Okay.
exactly.
I
Okay,
see.
what would you like to look at next? So this, what was this problem? Problem 6?
I'm okay. I understand the others.
You understand the
59,
others?
right? Yeah. Yeah, I understand the others.
Okay,
Like the general process.
so I would say that. Do you really feel comfortable with 2 and 3 at this point? Because I would say 1, 2, and 3 are probably the hardest on this page.
Okay, yeah.
Yeah. Do you want to look at one of those?
Let me check.
Yeah, because
Mm,
like the whole big theme for this
maybe.
one is trying to find the right substitution.
Yeah.
So I would say that 3 is a slightly harder version of 2. Like the definite integral part
Yeah.
doesn't matter too much, but having the 4 in there makes it just a little bit more confusing.
Yeah. Maybe 3.
Okay, sure.
Okay.
Sorry, I didn't mean to steal your thunder
No,
if
no,
you
no,
feel
it's
like you
okay.
understood. But I just, since we've are on a roll here, I just wanted to figure out what other problems. Also, because for the students tomorrow, I wanted to demonstrate to them, via recording.
Yeah, yeah, yeah.
Yeah.
I see.
So what is this? X square root of 1 minus 4x squared? Okay, so I'll write out the identities and I'll let you tell me which one makes sense. Squared x is equal to 1, tan squared plus 1 is equal to secant squared. Which one makes sense?
The second one, because it's 1 minus something.
You are...
I mean, the first.
Hold on.
Yeah, the first one. Sorry.
Okay, yeah, the first one.
Sine.
So, look, what
Yeah.
happened? This is a productive question, right? It is the first one, but what would have happened if you tried to force it to be the second one? It would be 1 minus secant squared is equal to
Yeah.
minus tan squared, right?
Yeah, that's
And this is nonsense because this is a tan squared is positive, so minus tan squared is negative, and you'd be trying to take the square root of a negative number.
yeah.
That's why you don't want to do it that way. That's why you got to use this one.
Yeah.
Okay. So, all right, let's try to make this look like 1 minus, do you want to do cosine or sine squared? Doesn't really
Sine
matter.
squared?
Sine squared,
Doesn't
okay.
really-
Okay, so this one is already nice for us. We don't have to pull it out, but we could always pull it out if it was any number other than 1.
Mhm.
But at this point, we need to match sine squared with 4x squared. Let me call it u instead, okay? We need to match sine squared of u with 4x squared.
Yeah.
And sine of u is equal to 2x.
Mm-hmm.
Cosine of u du is equal to 2
Yeah.
dx. Pretty good so far,
Yeah.
right?
Yep.
So, okay, let's plug these in. So I'm just going to ignore the... so what's x? X is basically sine of u
Yeah.
over 2 at this point. So I'll write the 1/2 in front.
Okay.
And then this turns into 1 minus sine squared, which is cosine squared. So square root of that just leaves us with cosine of u,
Mm-hmm.
right? And then dx
Yeah.
at this point is, what is it? Cosine over 2? Cosine u over 2 du. Starting to look pretty nice, right?
Yeah.
Yeah. I think you know what to do at this point, right? Cosine squared of u du, and I think it just turns into a 1/4 out front.
Mm-hmm.
Okay, so use your favorite u sub. By the way, let me mention something really quickly. U substitution. How would you solve a problem that looked like this? Sine of u, I don't know, cosine to the 7th u. Do you know how to do this problem? This is unrelated. This is an aside.
I would probably change the sine of u to 1 minus cosine u, or like bring out one of the cosines.
I see what you're
Like,
saying. So you would want to...
Negative one, so it would cancel out.
So I think that's making it harder than it needs be. This is sort of a trick question because this is a situation where we can still just do the exact same u substitution. U is equal to, let's call it v is equal to cosine of u, then dv is equal to minus sine u du. So as long as as long as like the odd one out is on top next to the du, this u substitution works out perfectly. The power of the other one can be on the bottom or on the top, right? This is basically cosine to the negative 7th. It really doesn't matter too much whether it's on bottom or on top is the point that I'm getting at here.
Yeah.
Yeah. Okay.
Yeah. Okay,
Good.
I get it.
In fact, that's probably how you integrate tangent, right? Now that I think about it, tangent is just sine over cosine. It's probably just a simple u sub.
Yeah.
Yeah. Okay, so that's an aside. So I want you to be super confident when you're seeing, a single power of sine with, any integer power of cosine.
Okay.
The other thing I wanted to mention is if you see like a sine cubed and then cosine to like some nasty power, like to the 10th or something, right?
Yeah.
The way that you do this is you break it up. 3 is actually a really nice number because this is sine of u. So you break out one sine of u, and then the sine squared turns into 1 minus cosine squared. And then you're left with a cosine to the 10th, right? So again, the sine basically, you can basically turn the sine cubed into 1 minus cosine squared. So, okay, when you distribute it, this becomes cosine to the 10th and cosine to the 12th, right? And then the sine u for either one of them is just there to soak up the chain rule, right? It helps you expand via chain rule.
Okay.
And of course, if this problem was instead cosine of cubed u and then sine to the 10th u, sine and cosine are super symmetric with each other. So this really is, the thought process is just basically the same. The computation is just slightly different because of some minus signs. Okay. Following me so far?
Yeah.
Okay. Yeah. Do you want to tackle the hardest problem on the set? Or how do you feel at this point? I think the hardest problem was number 1.
Okay, we can do number 1. Wait, give me like a minute.
Sure.
30 seconds, wait.
Oh, wow. There is 1 or 2 people who noticed the stream was on. Nope. Just met someone from UC Irving where some wanted to ask about some late night calc questions before a quiz or something. Just helping some quiz preparation with some new students. That's all.
Hi.
Hi.
Okay, I'm okay.
Sure. Okay.
Yeah. Okay.
So are you ready to look at question 1?
Yeah.
Okay.
For number 3, like
Sure.
just the, you just plug it back in and then you subtract it, right? Then there's nothing else.
For number 3? So
Yeah, for that
let me
one.
just solve it just a tiny bit more, right? So if we used u sub, so u is equal to cosine. Okay, so I guess it would be v subbing. V is equal to cosine. And dv is equal to minus sine u du. You would have to do a little bit of substitution here, right? But at this point, it would turn into, I think, minus 1/4 cosine of, minus 1/4, what is this, v dv. This is a very, standard integral. This just turns into v squared over 2 times minus 1/4. Okay, now I guess the hard thing is that you have layers of substitutions now, right? So this thing is equal, so, okay, you have to add like a plus c, minus 1/4. So when you sub it back in, what was v? V was just cosine of u. So this turns into cosine u squared over 2 plus c. Okay, now what was u? You got to sub it in again. You see, it's a bit of elbow grease. Okay. But
yeah, I see.
U was equal to cosine of. Sorry, what was u? U was what do we define it as? I lost my train of thought here. We said sine of u was equal to 2x, right? So let's draw our little triangle. So if sine of u is equal to 2x over 1, essentially, that's basically saying that the hypotenuse is 4x squared plus 1. So cosine becomes 1 over that.
Okay.
right? So
Yeah.
1 over 4x squared plus 1, the square root and the square root cancel out. And I think you're left with something like this, and then you got to plug in 0 and what, negative a half?
Yeah.
And yeah, that's the
Okay,
idea.
okay.
You can do that on your own.
Yeah. Yeah, we can do number 1.
Sure. So this time around,
Yeah.
I will try to let you take the lead, and I'll do automated calculations, but I'll try to let you steer the ship, so to speak. Okay.
Okay. My
Okay. So what
brain's
does this
kind of
look like
dead
to you?
though. My brain's kind of dead because I've been in school. I've been at school since like 7.
Oh, geez.
Yeah, that's why like yeah. So
I'm
that's
sorry to
why my
hear that.
brain's like fried. It's okay. Um,
By the way, you mentioned earlier that you were planning to pull an all-nighter. Please don't, if at all possible.
yeah, no, I was planning to like nap after this until like 3 or
Sure.
4 and just do like some problems.
Okay. Well, make sure you don't miss your quiz.
Yeah, no, I won't.
Yeah. Okay. Sure. So what does this look like now? Uh, I'll start by writing the identity as always, right? Whenever I see a constant plus or minus x squared, I'm gonna write out my identities like a good child, right? What does this look
Yeah.
like to you? Tan squared plus 1 is equal to secant squared.
Yeah.
What does this look like to you?
The second one.
Okay, I agree. So, okay, so this is basically going to be, I like writing it kind of close to it, but we're trying to make this into 1 plus tan squared of u, right? So tan squared of u is equal to x squared.
Yeah.
Right? So x is equal to
X is equal to
just tan of u. Sorry, I guess I was trying to make that your cue to speak, but
oh, sorry.
yeah,
Sorry,
I guess it's kind of a little bit hard to do that virtually. So maybe I'll just take the handle when it comes to just pure computation.
Yeah.
I get a little bit nervous because when I automate these parts, sometimes you miss out on the memory of going through these things on your own. Like I know by heart that the derivative of tan is secant squared u, but you got to make sure to do a bit of practice on your own to get that. All right, so dx is equal to secant squared u du. And then yeah, at this point you just plug it in, right? So this turns into, well, 1 plus tan squared is secant squared. Yeah. Square root of secant squared is just secant at this point. And then it's tan u on the bottom, right? Because x is equal to tan u. And then dx is just secant squared u du. So,
Super
oh boy.
Random question. Where
Sure.
does the square root go?
Where does the square root go?
Yeah.
Yeah. No, we made sure to cover that. So this turns into at some point 1 plus tan squared, right? Which is secant squared of u.
Yeah.
And the square and the square root cancel out.
Okay.
And that just brings you to secant u by itself there.
Yeah.
So what are we looking at now? We're looking at secant cubed of u over tan of u.
Yeah.
Du. And oh boy, this is where things get a little bit nasty. Did I make a mistake? Okay, so what is this? This is 1 over cosine cubed of u times sine cosine. Du.
Oh, and then you can cancel it. Yeah.
You can cancel it a little bit, but unfortunately it's still pretty nasty, right? Because this is 1 over cosine squared of u, 1 over sine of u, du. And if only the sine was up here, we would be golden. This would be so easy, right? Because then you could just use u sub by letting u is equal to cosine, and then du would absorb the sine would absorb the chain rule.
Yeah.
Right? But unfortunately, it's pretty darn nasty, and we got to think of something to do about it. And gosh, do I even remember what we were doing today?
With the cosine squared, can you use like the long formula, the cosine squared plus sine squared equal to 1?
I'm trying to remember if that would help us.
Because everything would be sine.
Yeah. So I mean, if you replace this to 1 minus sine squared u, well, the issue is that then this looks like, what is this, sine of u minus sine cubed of u?
Oh, okay.
And I think that's still pretty nasty. Gosh, what was the trick that we came upon earlier today? Let me double check. I don't want to wait around. Make you wait around looking at this thing.
Are you allowed to like bring it up?
What's up?
It's like 1 over sine u, right? Can't you make it like to the negative and then you du it, or does that not work?
Um, sorry, give me 1 second here.
Okay, go. That's okay.
Secant squared. Sorry, what were you saying?
Like it's like 1 over cosine squared and then 1 over sine squared, right? If you make it like, I mean 1 over sine u,
Sure.
if you like make it to the power of -1.
Yeah, but that's
Would
what I
that
was saying earlier. This would be so nice if this sign was on top instead of on the bottom, right?
Yeah.
But because it's on bottom, I don't see a good way to use substitution. Because if we let v is equal to cosine of u, then dv is equal to minus sine u du, right?
Mhm.
We really need the sine u to be right next to the du, but unfortunately it's on the other side of the fraction. And that just breaks everything. That just doesn't, we have no, I don't know how to make progress on this because of that.
Okay.
See what I'm saying?
Yeah.
Sorry, the trick was splitting up with secant squared, secant cubed over tan. This is hilarious. Why do I not remember how to do this? All right, secant cubed over tan. This is equal to secant squared and CSC du, right?
Okay.
Secant squared u.
Oh
Yeah, so we're getting into some really nasty stuff right now. But secant squared is just 1 plus tan squared u times CSC, right? And at this point, I think are we making progress? Sorry, my brain is also pretty fried right now, so I'm going to take a quick peek here. 1 plus tan squared, 1 over sine. So this is 1 plus sine squared theta over cosine squared theta. And this is 1 over sine. Yeah, this works out pretty nicely. So, okay, it's not that nice, but 1 over sine is one of our elementary integrals. I don't know it off the top of my head, but unfortunately, I think you'll have to. Because this is just the integral of cosecant, which is considered a basic trig identity, right?
Yeah.
But then this part over here actually becomes quite nice. This turns into sine theta over cosine squared, which is the formula we love so much, right? The what do you call it? This is the pattern we love a lot. And I think I started letting my u's and thetas get all mixed up, but I don't care at this point. I think I just switched from u's to thetas at some point, but it doesn't matter. This is not some substitution. This is just me getting tired and blanking and doing the wrong symbol. But you know how to do this, right? This is just a regular substitution. And this one right here is one of the elementary things that you should be able to find in your textbook, or it's considered a standard integral. And yeah, do we actually want to, try to write this out explicitly, or do you think this is good at this point?
I think it's okay.
Yeah, like you should have earned most of the credit for the problem at this point, I think.
Yeah.
Like if you wanted to do it all the way out, it's these really nasty terms, because again, you're going to integrate this and this is going to look like some crazy ln of something. This one isn't going to be quite as bad. But once you sub in the thetas again, I think our final answer that we got looked like, negative ln cosecant theta plus cotant theta. And then once we plugged all this back in, we got this abominable expression.
Okay.
Yeah.
Okay.
That's the idea.
So the ln came out because it's 1 over something.
Yeah, I don't exactly remember how to integrate this off the top of my head, but the integral of 1 over sine is this thing right here, this negative ln.
The integral of 1 over sine is negative ln.
Yeah, the integrative sine is negative ln cosecant theta plus cotan theta. This is that, like, it's considered an elementary integral, but I don't know it off the top of my head. You'll probably just have to look it up in your textbook. But for the sake of a quiz, I would probably just memorize it.
Okay.
Yeah, sorry. I realize that they're placing a lot on you in terms of just memorizing it.
No,
it's a bit unfortunate, but you probably need to memorize like 10 things for tomorrow, right? Or for your midterm is probably like you know, the
everything.
double angle formulas. There's also a double angle formula for sine, right? Sine of 2x is equal to 2
Yeah.
sine x cosine x,
Minus plus. Yeah.
right? You probably want to get the double angle formula for cosine. You're going to want to do the sine squared plus cosine squared identities. And then tan squared plus 1 is equal to secant squared. What else?
Okay.
The basic integrals and derivatives of integrals and derivatives of, I guess, just all these things, right? Like tan, like sine and cosine, obviously, those are easy, but tan, cotan, cosecant, and secant.
Okay.
Right? You're going to want to know integrals and derivatives of all these.
Okay.
Yeah, tan and cotan have nice derivatives. They just turn into secant squared and minus cosecant squared. But yeah, you're getting to, I think, probably the end of our session today here, right?
Yep.
Anything else you want to practice? Anything else we haven't gone over yet?
I think that's all. I think I'm okay for tomorrow. Maybe, hopefully. Yeah.
Okay. Sure.
Okay.
Well, I
Yeah,
guess I'll
thank
end that
you.
thing right there. Sorry,
Okay.
give me a second here. I'm ending the recording.